Good morning, my name is Billy Davis, and today I'm going to present my analysis of the iris dataset, exploring how species and petal length influence sepal length. We use two statistical methods, ANOVA, excuse me, to test for differences in the sepal lengths across species, and a linear model to predict the sepal length. Our goal is to understand the morphological differences in the iris flowers, which could inform a botanical research. Let's get into the data. For our task one, our ANOVA analysis, we're going to perform a one-way ANOVA to check if the mean sepal length differs across the three iris species, the Septus, versicolor, and Virgacina. The sepal length is our continuous dependent variable, and species is the categorical factor. This box plot down below, let me scroll down. The box plot down below show the sectose has the shortest sepal length around 5 centimeters, while the Virgacina is the longest near 5.6 centimeters. The ANOVA results give an F statistic of a 119.26 and a p-value of 1.6 e. That's going to be far below our 0.05. The Violin plot confirms the distinct distribution of the septose tight spread. This means that we're going to reject the null hypothesis, and there are significant decreases in the sepal lengths across the species. The larger F statistic indicates a strong group difference, suggesting species plays a key role in the sepal length variation. Next, we're going to go into our linear model development for our task 2. In task 2, we built a linear regression model to predict the sepal lengths using the species of the petal length as a predictors. Here you're going to show on our scatter plot, you're going to show the sepal length versus the petal length, and it's going to be colored by the species with the fitting lines for each. The model's R squared is 0.867, meaning it explains 86.7% of the sepal length variation. The F test and the p-value of 3.63 confirms the model significance. The key coefficient versicolor sepal length is 1.054 centimeters longer than the setosa, and the Virginius is 1.529 centimeters longer. Holding the petal length constant, each 1 centimeter increases the petal length adds 0.753 centimeters to the sepal length. You're going to show that in our residual plot. That's going to show no clear pattern, suggesting it is a good fit. This model is going to be robust and predictive, highlighting both species and the petal length as an important factor. Next, we're going to go into our task 3. It should be our assumptions and limitations. For our task 3 assumption and limitations, we're going to have our ANOVA to assume normality, equal variances, and independent observations. The linear models add linearity to multicollinearity. This is going to be our QQ plot and a Shapiro-Wilk test of P 0.05. It's going to suggest the residuals are roughly normal. Let me scroll down a little bit. I'm going to show that our residuals are roughly normal. Our Levine test of P 0.05 supports equal variances. However, violations could occur in the data sets. Non-normality might inflate errors. We'd use transformation like log and norm parametrics. Tests like the Krukau-Wallis and unequal variances could be biased results. Each of our ANOVAs multicollinear checks for the VFA wasn't here. It should be distorted. Coefficient is present. Some of the outliers we do have in our data set are small and also unreliable results. For the Python tool, we use Scrippy Stats for a test and stats model for our robust model, which is going to help us diagnose and address these issues, ensure validity, valid conclusions. As you can see here for our outliers. And for our task 4, our mini project, and our task 3 is going to explain the assumption limitations, and our ANOVA assume normality equals variances. For our task 4, our mini project, we're going to ask ourselves the questions: how do species and petal length influence the sepal length? ANOVA confirmed significant differences in the setosa shortest and the Virginia the longest. The linear model with 86.7 R-shape shows the species and petal length strongly predict the sepal lengths. Limitations include potential normality and various issues addressed via diagnostic tests or robust models. These findings suggest distinctions among our iris species. Useful for classification or ecological studies, the model predictive power could aid automatic measurement systems. For our future work, this includes post hoc tests and pinpoint group differences, or adding predictors like petal width. In conclusion, our ANOVA test and linear regression model robust insight into our iris morphology with practical application and botany. That is going to be it for my topic 7 DQ2. DQ, it's not a DQ, it's our analysis of variance and linear model. If there are any questions, please reach out. Have a great day.